Right, welcome to the second talk of this morning. So we are going to continue with the Microsoft invasion this morning, and we now have Ching and Cheng from the Redmond group, and he's a senior researcher there, and he's going to talk about game-theoretic approach to reinforcement learning, offline reinforcement learning.
Yeah. Do I need to use this?
You have a minute.
Okay. So hi everyone, so I'm Ching-An. I'm from the robot learning group in Redmond. So now I'm going to switch the topic. So didn't talk about interactive learning for decision making, right? So here I'm going to talk about something that's not interacting at all. So this is the approach that we have for offline RL. So before I start, I want to thank my co-authors. So Tenyang, Nan, Paul, and Alec. They all contributed greatly to this project. So the main motivation of this work is trying to make this, sequential decisions in real-world problems. So this includes applications such as building healthcare systems like virtual assistants or robotic systems. So in theory, we think that RL is a very nice framework designed to, let's say, learn policies for interaction, and it's ideally for the application like this. But in practice, it faces various kind of difficulties when we actually try to apply it. So we know that RL needs a lot of samples and computation, but in addition to that, one key challenge that we found in practice is that the data we can collect often do not have enough diversity or coverage that we need in the theory. And that is because that the decision you make in real world often carry real consequences. As a result, we cannot run just the exploration policy or a random policy to collect data, but often we can only use a policy that can, let's say, meet certain requirements such as safety or being ethical to collect data. And that significantly limits the data diversity that we can collect. As a result, we need to think about a way to design algorithm that can deal with such a systematic bias in the data distribution that we have. So this brings out the framework of offline RL, which is designed ideally to learn policy regardless of the data distribution. And so this is nice, but it's a very difficult question. And the core difficulties come from that ideally, certain idea, but in general, if we don't have enough data coverage, then it is impossible to estimate even, let's say, how a policy will perform. So we kind of lack the objective, right? So now we are talking about how to optimize policy without objectives. So just give you an example. Let's say I want to learn a safe driving policy, let's say for taxi, but all the data I collected are safe driving behaviors. So now I have a candidate policy. I want to just even to figure out whether that's a safe or not safe, and that's just not possible because there's no unsafe driving examples in my data set, right? So this is a fundamental issue that we have in offline RL. So the good thing is that we kind of have nowadays have a principle to deal with this issue, which is the idea of pessimism. So here the main idea is to let the agent to think about the worst case for the scenario that we don't have data, and we can choose to optimize for a performance lower bound instead of the true performance, and that's something we can estimate. But this is not a full answer because there are many different ways that we can use to define what we mean by worst case and to construct the lower bounds. And different choices will have different trade-off between conservatism and generalizations. Let's go back to the previous driving example. So suppose that we let the agent to imagine the worst case outcome, such as the car is going to crash onto the road. And if the agent just deviates slightly from the action is in the data, then the agent trained this way will just basically tend to overfit to the data that we have and will not know how to behave if we put it under a slightly different traffic condition, right? And on the other hand, we also don't want the agent to just naively believe that actions not covered by the data are always good actions. So the main purpose of today's talk is to introduce a different perspective and of offline RL, which is this game-theoretic approach. And we found that this perspective has been very useful to us in clarifying some of the difficulties and complexities of offline RL and just make it very simple. And this framework can also be used to systematically design new offline RL algorithms. So the key idea here is to frame offline RL as a two-player game between the RL agent and a fictitious adversary, whose role is trying to model the uncertainty due to missing data coverage. And so when given with a policy from the learner, the adversary basically would choose a hypothesis from a class of hypotheses, and such that it will give the worst case performance estimate. So these hypotheses, you can think about, they are, let's say, models of dynamics or models of value functions in RL. And we show that if we let the learner to optimize the lower bound constructed in this adversarial way, then the learner can have a provable guarantee in terms of performance, even when there is no, let's say, assumption on the data coverage. So if we compare this framework with, let's say, other approaches to offline RL, one of the main advantage here is that here it allows to kind of very systematically reason about the lower bound in a way that is consistent with our prior on the hypothesis class. And so this is very nice because that now we will have a very natural trade-off between generalization and conservatism. So for example, if the learner takes actions that will lead to scenarios where our hypothesis class, which are function approximator that cannot generalize, then naturally this lower bound will become conservative. Because in that places, the adversary have like stronger power. On the other hand, if the agent visits some places which our functions can predict well, then the lower bound will naturally be tight, even though those are the scenarios where we have like very low or zero data density. So, so what it means as a whole is that if we train an agent in this way, it can essentially leverage the generalization ability of our function class in this hypothesis class to kind of like learn policy that can generalize to like a wider set of scenarios beyond the data coverage. So yeah, so the outline for this talk. So I'm going to first introduce this like game-theoretic framework, a little more details to be more precise. And then I'm going to talk about two different versions of it. One is based on absolute pessimism, and the other one is based on relative pessimism. In particular, I will show that the formulation or the version based on relative pessimism has a very nice property that we call robust policy improvement. And what it means is that if an algorithm has this property RPI, then the policy learned by the agent can provably be better than the data collection policy, regardless how we select the hyperparameters. So this is a very nice property in practice because like selecting hyperparameters purely offline is a very difficult problem. By the way, so feel free to interrupt me if you have any questions. Okay. All right, so let's try to make the problem more concrete. So in this talk, I'm going to consider the typical MDP setting. So this S is a state space, and you take an action, go to the next state, and followed by this Markovian transition kernel, you get the reward. And so we assume that, and we're going to consider the infinite horizon discounted version of this. So since we are going to consider offline RL, I'm going to assume that we have a data set collected by running a behavior policy in this NDP, and starting from some initial state S0. So we assume that this S0 is known to the agent, but you can relax these to, let's say, to have an initial state distribution, and then you have some samples of that. So this is just to make the presentation cleaner. And the goal of the agent is trying to find a policy to maximize the discounted return, which is defined like this by the reward. And it has to do so without ever interacting with the environment, but only looking at this data set collected by the behavior policy. All right. So in this talk, I'm going to focus mostly on the model-free version of our framework. But at the end of the talk, I'm going to give you some hints about how you can easily extend this to the model-based one. And so since I'm talking about model-free, I need to define some notation for that. So I'm going to use tpi to define the Bellman backup, and use qpi to denote the Q function of a policy. And just as a reminder that the return want to optimize is equal to qpi evaluated at 0 and pi. And I'm going to assume that the agent is given with this function class, capital F, of function of state and action. And this function class will satisfy the common assumption that we need, which is realizability, which says that the qpi belongs to this function class, or in the completeness assumption, which means that the backup of this function class will also be within this function class. And this assumption can be relaxed to be the approximative version as well, and things will go through. So I'm going to make the exact one so things are clear. So our two-player game is formally a Stackelberg game. So what it means is that it's a sequential game between a leader and a follower. And in this game, the leader will place the first, and the follower will place the second after observing the decision made by the leader. And so this is a generalization of the zero-sum game in the sense that now these two players can basically optimize for different objectives. rather than the opposite of the other. So each game here is defined by an objective phi and then a regularization term E, which is forcing data consistency. So we let the agent of the R algorithm, which is a learner here, to be the leader, and its goal is trying to optimize policy to maximize a lower bound constructed by this adversary. On the other hand, we let the adversary to play the second to be the follower, and so we will try to basically when it sees the policy from the agent, it will try to find a hypothesis, which in our case will be the function of state and action, the value function, to minimize this sum of code. So we have the objective phi, which both players compete, and plus a regularization term that will enforce data consistency. And here beta is essentially the hyperparameter that control how consistent we want the hypothesis to be with the data. Okay. So this might sound a bit like kind of abstract. So let me try to introduce the first example of the version of our algorithm that I'm going to talk about in the first half of the talk. So this algorithm is something we call the absolute pessimism game. And this is defined by this particular phi and regularization. So since we are talking about model-free algorithm, about like learning values as our hypothesis class. So this using the Bellman error on the data set or data distribution will be a natural candidate to be, let's say, to force this hypothesis to be data consistent, right? This is how it is defined. So on the other hand, the reason why we choose this particular phi is because that we want to optimize for the performance, like the return J of pi. And we know that J of pi is equal to Q of pi evaluated at 0 and pi, right? And if you see this takes the exact like algebraic form as the phi we choose up here. If we just replace, let's say, f with a Q pi here, we get the same thing, right? And so by this algebraic equivalence, and then we can show that by property of this like two-player game, which we call the pessimism lemma. Then if we use this equivalence, then the player in this two-player game, sorry, the learner in this two-player game will be essentially optimize the lower bound of the performance that of 0 pi.
You should just think of F as Q.
Yeah, so think about F as estimation of Q or guess of Q. Okay. And then since we're optimizing lower bound, and then by the optimality of like optimizing lower bound, right? So we are basically computing, let's say, the worst case. Then you can easily show that it's similar to the reverse of like UCB proof. So you can show that now you can have a regret guarantee with any comparator. And now the gap of this regret will depend on basically how well you can estimate the comparator's performance with this pessimistic evaluation step, right? So you can now think about that. What it means is that if the comparator can be well estimated by the data, then the policy learning this approach can essentially have like small regret with respect to that comparator. And this is kind of what we naturally hope for offline RL. Any questions? No. Okay.
One question.
Yeah.
So about the phi objective for the learner,
Yeah.
Or for the leader. So does the phi already incorporate the minimization from the adversary perspective? So when you try to map to your original the game formulation,
yeah.
So the phi already incorporates the mean.
So definition of phi alone is a phi function of pi and f together. So that definition doesn't incorporate the minimization. But the learner will optimize phi evaluated at f pi, where f pi includes the minimization.
I see.
Okay. So let me use a visualization to kind of help you to kind of understand how this two-player game works. So here we consider like a offline banding problem, which is like a very special case of offline RL with polarizing equal to 1. And the way I'm going to discuss this is trying to compare this absolute pessimism again with a more common approach to offline RL, which is called point-wise pessimism. This is essentially the principle that is behind algorithms that use boundaries or truncation to be, let's say, pessimistic or to construct the upper bound, lower bound. So in this example, I suppose that there are two hypotheses that are data consistent, just for simplicity. And so if you think about lower bound and based on the idea of point-wise pessimism, then essentially what it does is that for every action that we're going to pick, we construct, let's say, yeah, between these two hypotheses, what is the lowest value, and do it point-wisely, and then we get this red objective, right? So we can basically optimize this red objective and get a policy that is maximizing it. And by doing so, we can kind of guarantee similarly that the learn policy can compare with the best policy that can be explained by the data, because it's also optimizing a lower bound. But there's a one caveat in this common approach, which is that as you see in this figure, this red objective does not belong to our hypothesis class, which means that the agent can potentially be optimizing something that is overly pessimistic. And for example, in this toy problem, we know from the hypothesis class that either taking like very small actions or taking very large actions can be bad, but they cannot be bad simultaneously. But these red lines suggest that like both of them can be bad, right? So this, if you turn into, let's say, the real theory, what happens is that you will largely increase the size of, let's say, adversary hypothesis that you have to compete with, rather than the one you started with. On the other hand, this game theoretic approach would directly optimize for hypothesis within your prior class. And it goes trying to find a policy that can work well with either of these hypotheses. And in general, this will lead to a stochastic optimal policy because of this adversarial nature of training. On the other hand, for the pointwise version, it's likely to lead to a deterministic policy. But the benefit of the approach on the right-hand side is essentially that because we are dealing with directly the original class of hypothesis, which have our prior about the problem, the learn policy can basically generalize better and be less conservative. So now we kind of understand that the basic about how these two-player games work. So let me show you how we can kind of solve this problem and get a policy from it, right? Because what I talked about are very like information theoretical so far. So the main idea we're going to have here is an optimization algorithm based on the a very famous no regret and best response reduction in online learning. So this is an iterative algorithm. So in every iteration, we have a policy from the learner. We are going to first do a pessimistic policy evaluation step, which is basically calling an oracle to solve the objective function, basically the optimization problem of the follower. And once we do that, we get a hypothesis F, which in our case, again, is this function of state and action, which kind of is an estimation of the Q function. So now the next step, given this F, we're going to call a no regret optimizer, and to basically treating this F as a utility function in an online learning problem. And so one thing you can use, for example, would be, let's say, follow the regress leader, and this will lead to the update rule that like this. And we're going to repeat this process for k iterations. And at the end, we let the learner to kind of like output the uniform or mixtures of policies generated by this iteration process. So this is a policy that the learner is going to output at the end and apply to the real environment.
Sorry, what do you mean by no? Like you treat this as an online.
Right. So basically, so I didn't write it specifically here, but the idea here is that given an F, every round you get an F, and then we define online learning problem for every state. So F is a function of state and action, and we treat F, fix a state. Now the function over action is kind of, we treat F as a utility over those actions. And then so every round you get different F. So it kind of like an online learning problem with kind of like adversarial utilities. And you want to have no regret for every state with respect to that sequence of utilities. Okay, so this part is like a full information online learning problem, but just with potentially like changing laws. Okay. And for the absolute pessimism, again, I talked about earlier, this algorithm is known as pessimistic soft policy iteration. And this is computationally efficient, preferably if the MDP is linear, because these two steps can actually have closed form solution.
Is this like a no regret implementation of the greedy step?
Yeah, you can think about like that. It's like yeah, so let's say if you do the typical, let's say, policy iteration, you want to, let's say, directly maximize the value with all the critic, right? But here, because these are critics being chosen adversarially, and so it will change across, it kind of sort of like witness different NDPs during this problem setup. So you want to kind of run like the optimization algorithm that is robust to this adversarial sequence. And that's why we need to, let's say, not really do a hard max, but kind of doing a soft max here. if you think about that. Any other questions? Okay. So now let me show you like the exact theoretical guarantees that we can have for this absolute pessimism. So here we show that if we make the assumption of this function class f satisfy the realizability and complete this assumption, then we can show that when we choose the right beta value according to this formula, then the regret of this learned policy, which is this mixture of like policies that we generated during the optimization, will have a regret bound to any comparator, and this upper bound have 3 terms. The first term is the common statistical error due to concentration. The second part is what we call the outlier support generalization, and which is measured in terms of the Bellman error of the hypothesis that it chooses during optimization. The important part about this expression is that we only measure this error at the basically state and actions where our function class cannot generalize. So this can be potentially like smaller than, let's say, places where we have low data density. And this is reflected in this more generalized definition of concentration coefficient C. This is kind of like the formal way to show that, yeah, we are leveraging the generalization ability of our function class to reason about what is being in support or cannot generalize versus out of support, rather than just like viewing that, defining that based on the data density. And finally, we have this optimization error, and this comes from this no regret part of this, let's say, no regret and best response reduction. And so if we, let's say, update the policy by a no regret optimizer, and if that, what it means is that the regret will be sublinear in optimization, then this part will essentially vanish as we run more iterations. So let me give you some like high-level idea about why that performance guarantee is true. So we'll only take 3 slides. So the first thing we do is that we just substitute the definition of this mixture policy. So that will be an average of this like the sequence policy that we generate. Then I'm going to add and subtract a bunch of different terms. So I'm going to define something called RK, which is you can think about as like the effective reward that this hypothesis FK, which is adversary chosen, witness. So this is a FK. So it's a reward such that FK is a real Q function of this policy. And we also add and subtract the lower bound that we estimate, which is this F. So now we have 3 terms. And I'm just going to rewrite that in a nicer form. So the first term can be written as a Bellman error of this FK evaluated at the comparator's distribution. The second part, if you rewrite it, then it can be written as a regret in this online learning problem created by optimization. So here, basically, FK is being used as a utility, and this pi is essentially a comparator policy, basically for every state in this online learning problem that we create during optimization. And then the last term is the difference between our lower bound and the real one, right? So because we are doing a lower bound estimation, so this part will be negative. And then we can just split the first term into 2 parts, into the in-support error and out support error of the Bellman error. This is how we get this. And this regret part can essentially be upper bounded by the regret upper bound of our optimizer. And that's how we get the entire thing. Any questions so far?
Where did the lower bound come from exactly?
Oh yeah, so we are doing the So because we choose this objective, and so when we actually solve this pessimistic, let's say this adversarial evaluation step from the adversary, basically we can show that this phi under this f pi chosen by the adversary will form the lower bound of the performance.
So the adversary's choice.
Yeah.
Okay.
Right.
Explain the first term. The red term, can you explain that?
Right. So basically, the red term has essentially like the expected Bellman error under the distribution, right? So you basically split that expectation onto 2 parts. Like one is under a set that we have, let's say, low error, and the other one is under a set that we have a higher error, which is our subproperty, right? So like potentially the sum over, like weighted sum over, let's say, this error with weighted by the, let's say, this distribution, right? Just like split the sum into two parts. And for the parts which we have, let's say, kind of higher confidence because they are closer to the data distribution and closer to basically the region where our function kind of agrees. And that's kind of where we kind of have the, let's say, the typical regression, let's say, error, which is this insubpar part. And we kind of basically rewrite the part that is, I mean, that we cannot control as the outer subpar part. And so this is this like split is something that you can choose kind of like in the hindsight. It doesn't require, it's just like an analysis tool. And that's why we have these two terms.
The mu is the
The mu, where's mu? So mu is supposed to be the behavior policy.
New here is
New. Oh yeah. So I kind of like omit that. So new is any distribution that can be generated by some policy. So yeah. So this is like a little bit informal in the sense that like in the real expression you can kind of like choose this new in the hindsight.
like the words.
Yeah. So new is defined to be like this.
The words.
So essentially, they are defining as like the distribution such that like your error can be translated from, let's say, from the data to that new distribution. Yeah. So everything seems to be very great, right? So we can solve the offline problem. We kind of like can have like learnable guarantees. So what is really missing? What should I talk about in the second half of my talk? So if you pay attention, like the guarantee I've been talking about relies on a critical fact, which is like selecting the right hyperparameter beta, right? And this beta depends on, I don't know, many things I don't really know, like such as the real measure of this like complexity of my function class, etc. Right? This is not something I can actually get in practice. But when we choose the wrong beta value or say it right or say incorrectly, we actually lose all the guarantees into a degree that we cannot even guarantee that the learn policy will be better than data collection policy. And everything like this is very strange, since because you can use this behavior policy to collect the data, then this is something that is already like kind of working, right? So you want to only do learning to get something that's better than what you had at the beginning. So this makes the algorithm very unreliable. And this is not really the fault of this particular design, but in general, it's a fact for any algorithm that is trying to optimize for LCD.
Which part of the proof use the choice of beta?
So in this proof, I need to kind of choose a beta to actually get this like tooth error specifically. And I also need a beta to kind of like, I need the lower bound part, okay, yeah, but
right, like there.
Yeah, the beta.
The less than equals.
Yeah, it's hidden. Yeah. So this part is okay. This part can work for any beta, but the part that about like the exact size of this matters in the beta case. When we actually want to, let's say, basically want to show that the Bellman error is very small, but we do not minimize Bellman error directly, right? We minimize the sum of Bellman error, which is this E, and the other terms. And this controlled by beta. So we need to factor into the effects of how beta is and then to control how exactly Bellman error will be, right? If I set out, let's say beta to be 0, then it's not going to minimize Bellman error at all, and therefore like this like error of Bellman error term will be huge. If that is very large, we essentially like you can think about that you are over constraining your function class, and then that will kind of not include the true one, and then you lose the guarantees.
And that will come in the vector?
That will kind of like increase the essentially the you basically will be overfitting to the data, and then it will essentially still increase this like error in a different way. So basically this error, you get this expression at the end by basically balancing the beta, and that's how we got this final expression. And at the end, the way we balance the beta is to choose this particular form. And this roughly think about it, essentially like if you think about this as a doing a constraint, I want to constrain, let's say, two functions that are, let's say, have that low, let's say, error. right? If I set this epsilon of this constraint to be too large, and then there will be, let's say, too loose. If I set it to be, let's say, too small, then it will kind of exclude the true function, right? And this kind of is the same rule of beta, right? So essentially, if you set this LCB to be incorrect or be too not very precise, then essentially the regret that you get will essentially have this error depending on this part. And if that's too loose and to a degree, then you lose any guarantees. That's the issue. And the thing I'm trying to argue here is that in practice, it's very hard to kind of set that to be precisely right as what we want from the theory. In theory, you can do that, but it's hard to do that in practice. Yeah, and this is not really it's a kind of a generic issue of using LCP and to optimize performance. So the question here is, can we design an algorithm for offline RL that is more robust to such a choice of hyperparameters? Because as I mentioned that, I mean, a fully offline setting, I don't really know how to select this hyperparameter because I cannot interact with online, with the environment to really try out whether this hyperparameter is good or bad. So the idea that we have is to change the objective from the original phi, which optimized for 0 pi directly, but now instead to optimize for the performance difference between 0 of pi and 0 of mu. So we have the same regularization, but we change the differential of phi. And the reason we come with this new expression is similar to the reason why we used for the previous one, which is that this expression has the same algebraic form as this performance difference that we want to optimize. And this equality is known as performance difference lemma. So it's due to this algebraic form. So you see that since now we are only changing basically the objective by let's say a constant offset, and we are still using the same algebraic argument about choosing this objective phi, you can naturally expect that all the things I talked about earlier will go through, right? And then to a degree at the end, we can show that this no regret and best response scheme can also be used to solve this relative version of the game. And this algorithm is known as a TAC, or adversarially trained active critic, which is an algorithm that we proposed in ICML this year. And so you might think about that, yeah, I just changed the objective from the absolute one and to a constant offset, like a regret to the behavior policy. Why should that matter? Because I know, let's say in online RL, optimizing for the policy performance directly or optimizing for the regret, they are exactly the same thing, right? But the important thing here is that they are completely different in offline RL. And the reason for that is because in online RL, the agent can explore to reduce the uncertainty due to, let's say, finite data or just partial data. But in offline RL, you stick with whatever data set that you have at the beginning, and the uncertainty cannot be reduced. And that's why different choice in the objective will actually lead to very different results at the end. So before going to the math, let me give you some intuition about why they're going to be different, right? So suppose that you want to go to school and you have different options. You can take a bus, you can walk, you can bike, but depending on the traffic condition, they might take different amount of time. So if you have a very nice traffic, taking a bus will be much faster than the other options. On the other hand, if the traffic is bad, they might take the same amount of time. So now if I want to optimize my efficiency to go to the school, if I consider the worst case in the absolute sense, then all the three options will have the same worst case, which will be 30 minutes. And so taking either of them will be the same. So this is why you will conclude if I want to find a decision that is minimax optimal in the worst case. Okay. But on the other hand, if I try to optimize for the relative performance to taking the bus, then we'll have a very different conclusion. So here you'll see that the bus is the favorable option, because for the other one, in the worst case, they can be slower than taking the bus, right? Because in the worst case, basically within this different hypotheses. So in this case, it will be clear that we should take the bus, and this is kind of maybe consistent with our common intuition in this scenario. And so far, the point of this exercise to tell you that there's a difference between these two objectives. I haven't shown you why the relative one is better here yet. So, but you now can kind of get a sense about even I just shift the objective by a constant, but because of there's uncertainty in this hypothesis class, which is due to missing data, there is going to lead to a difference in the solution that you pick at the end. Any questions?
Incorrect for case one.
What?
The numbers are incorrect for case one.
Oh, really?
It should be 25 and 15 for.
Oh, yeah.
So,
yeah, thanks. Yeah. All right. So let's go back to the previous slide. So we now know they are different. So now let me dive a little bit deeper and to compare the, let's say, the properties of the two. So I'm going to compare that in terms of the lower bound they're optimizing and performance guarantee that we can get, right? So this is following the logic that I discussed about the absolute pessimism case before. So first, they are all optimizing lower bounds. Since on the left-hand side, we're constructing lower bound for the absolute one, the phi based on the expression of the absolute performance is optimizing the lower bound of the absolute performance. For the right-hand side, since I did that for this difference, and naturally you can show that like it's optimizing for a lower bound of the performance difference, J pi minus J of mu. And then similarly, by the optimality of optimizing lower bound, you can get a regret guarantee to any comparator based on essentially how much you underestimate the comparator. Right, so we have seen that the left-hand side, you have an underestimation error in the absolute performance. And naturally, you expect that now we get a lower, upper bound of the regret as the underestimation error for the relative performance of these comparators, which is del pi prime minus J of mu. Right, so everything has very natural like extension from the absolute case to the relative case. But in addition to that, there's one critical property that the absolute one doesn't have, which is this robust policy improvement property, or RPI. And this follows from that the fact that this relative one is optimizing for a lower bound of the relative performance. And so this kind of basically follows from the fact that I'm going to be, the solution is like minimax optimal for the lower bound, for the relative lower bound. And so basically it shows that for any beta greater than or equal to 0, at least for this population version, the learn policy is always going to be no worse than the behavior policy. On the other hand, we don't have that for the absolute pessimism. You have to pick the right beta value in order to compete with the behavior policy. Okay. We can also understand why we have this like robust policy about like no policy degradation from a different perspective, which is through a connection between imitation learning and offline reinforcement learning established by this relative version of the game or attack. And the main idea is that, so in this game, we have an actor and a critic, which is a policy and this hypothesis. So we can think about this actor and critic as a generator and a discriminator in, let's say, again, like a generative adversarial network formulation of the imitation learning or imitation learning based on like IPN. And by choosing different beta value, we can essentially control the strength of the discriminator. So for example, if I set beta to be 0, which will be completely removing this Bellman regression term. So this will be essentially rough, like kind of doing imitation learning with an IPN or with a Wasserstein distance between the distribution of the data and our policy, right? So in that case, the adversary will be the strongest, and the only way to compete with such an adversary will be to mimic the data exactly. Right, so we see that even when beta is equal to 0, we recover the behavior policy, and that's why there's no degradation. On the other hand, when we increase beta, we're going to weaken the discriminator to let it to be more data consistent. And in that case, we recover the offline error behavior of, let's say, this algorithm. So in other words, we show that there's a connection between basically equivalence between offline error with like relative pessimism, and that is equal to like imitation learning with a Bellman regression on the basically on the discriminator. And this is essentially why we get this RPI property, because regardless how I set the beta, it kind of will kind of reduce to the very natural sense. All right, so let me present the formal guarantees that we can have for this relative framework. So firstly is the regret, but I'm going to save you the trouble here and just to tell you that this page is exactly the same as what I show you for the absolute game. So you get the same guarantees as the absolute pessimism, which means that if I pick the beta value to be right, I can compete with any data, cover policy as the other offline algorithm can do. But now we have this extra property, this RPI property, and basically shows that if my beta is not super huge, it has to be sublinear in number of samples. I'm going to tell you why later on. And because now we have in the finite sample case. So if beta is not huge, then I can compete with the behavior policy up to some like statistical error and optimization error. Okay.
Is behavior policy something special here, or if suppose I had another policy whose performance I know, could I use that?
Oh, you can use, yes, that's a very good question. So you cannot do that with the model-free version, but you can do that with the model-based version. So in model-based version, I can have this RPI property, not to the behavior policy, but to any reference I want. Yeah, that's a very good question.
I need to know F for that. Like I should be able, like I should have some idea about F5 for that reference.
Oh, so you need to have a function. So as I mentioned, you can only do that in a model class, a model-based version. So what it means that what you need is that you need that reference policy. That's something that you can run. And you need to have a model class that kind of contains the true, let's say, NDP.
I know F5 for that one.
Yeah.
I know the performance.
Yeah, but that would be not sufficient. And the reason for that is because that you want to kind of like when the adversary picks this hypothesis, you want to make sure that you are evaluating, let's say, your policy and the thing you are comparing to under the same hypothesis. Right. So if you only know the, let's say, let's say the Q pi for the thing you want to compare with, which is a baseline. But when you pick the adversary, so when the adversary pick, let's say, the Q pi or the F pi for your learner's policy, if they are kind of like belong to different NDPs, then you don't have a way to argue that they are going to be comparable in the worst case. It's important that like when you're doing this optimization, you're optimizing for a relative error, and this is defined under the same potential hypothesis that this adversary is picking, and you're trying to pick the adversary, pick the worst case hypothesis such that there are differences that are obvious. Right. So, and then for this RPI property, one nice thing is that it requires even a weaker assumption on the function class F, which is not requiring this like completeness assumption. And the intuition here is that because we already seen that this RPI property mostly comes from the imitation learning behavior. So imitation learning basically throw away the boundary regularization term, and completeness is essentially needed for that term only. So so you can basically get an extra robustness in terms of like function like error that you have. So a quick proof of this is like this. So again, I'm going to just substitute the definition of my mixture policy. And then I'm going to add and subtract the lower bound I estimate about the relative performance. And then I'm going to expand the definition of phi to its original form. And now we have two terms. So the thing on the green one is the regret, which is the same thing we saw in the like the absolute version as well. This orange thing is essentially the difference between the true performance difference and the lower bound that we estimated. So ideally, this term should be negative because we are constructing a lower bound, right? But there are some residuals in here, and that's because that this phi is defined under the data distribution, and we have to approximate it by samples, and that's why you have this extra noise in here. So if you adopt a model-based version, this orange term will disappear. But for the model-free version, you'll pay for something like this because it's not exact lower bound. It's a lower bound approximated by further approximated by samples. What is the DFI? Oh, DFI is the complexity of the function class and the policy class. So let's say it's a log of, let's say, number of functions that you have, roughly, or the covering number eventually.
Okay, so the sum of the complexities. So.
Yeah.
I see. Okay.
All right. So just to recap what we have covered so far. So I talked about two different versions of this game-theoretic approach. One is based on the absolute pessimism. The one is based on the relative pessimism. So if you think about this, like different kinds of pessimism, they actually have like their counterparts in a more common, let's say, a single NDP approach. By a single NDP, I mean that I construct an NDP that is more pessimistic than the original NDP and optimizes my policy in that NDP. So for the relative one, the counterpart will be something called behavior regularization, which are algorithms that kind of penalize a policy to stay close to the behavior policy, for example, using KL divergence, or adding some, let's say, imitation learning term. And these algorithms all have the RPI property. They are more robust to hyperparameter selections, and really because of their, let's say, connection to imitation learning. On the other hand, we have algorithms based on like absolute pessimism that, as I mentioned, that will include algorithms based on using negative boundaries or truncation. And overall, we can think about this game-theoretic approach. Versions of these algorithms are less conservative because they can better leverage the structure of our prior on the hypothesis class. But they pay a price, which is that like you need to solve a two-player game, which is a much harder problem than just like optimizing, doing a single optimizing and solving NDP. And that's kind of the issue here. But suppose we can solve that, right? So here I'm going to show that like beyond theory, we actually show that this idea of like no regret and best response can actually be used to design something that's runnable in practice and can achieve the state-of-the-art empirical performance in offline R benchmarks. And the way we do that is that we're going to approximate this update rule by stochastic gradient update rules, and with two different time scales. So we're going to basically take gradients to optimize these two objectives, where the no regret will be replaced by maximizing the critic. But I'm going to basically let the critic to take a much larger step size than the actor. So this is kind of to mimic the behavior of the best response. So given an actor, I want to kind of find the hypothesis that is the most pessimistic with respect to that actor. Right, and in the experiments, we use like a step size that's like 1,000 times larger than the actor. So you can think about this: like actors are updating very slowly, and the critics is much faster. And with this, we can actually use this algorithm to train deep neural networks, and we compare that with other state-of-the-art like deep offline R algorithms, and just head-to-head in the empirical performance. So after this arrow, I don't have any theoretical guarantees about what it works. But it's a kind of like an empirical algorithm that is based on the idea of what we can prove. Okay. So we run the experiments on the D4L data sets, which have, and then we pick 24 data sets from that benchmark. Then there are like data sets of continuous control problems of different dimensions and have different data qualities from data collected by random policies or extra policy or a mixture of multiple policies. And so first we found that this PSPI algorithm based on the absolute pessimism kind of like is almost the state of the art. It kind of wins almost all the baseline in most cases. And we found that if we use a relative version, it's even better. It beats even all the baseline in almost other cases. And we get a like 9% improvement in the performance among, it is for like more than half of data sets that we tested. No, so in the empirical version, we train neural network policy and we just use the last one. Yeah.
So each problem to optimize.
Yeah, and I use a mixture. Yeah.
Numbers better here.
Yes, so it's the next one.
Yeah. And earlier, the theory suggested, of course, we are departing that area, but that we're going to compete with the behavior policy at least, but we see a bunch of cases like relocate human, where this is absolutely not happening.
Right. So you see most of the cases they are better than behavior policy, but not for the human case. Right. And the reason is because here we're using Markovian policy, and this data set is collected by human, which is not Markovian. So there's a big mismatch.
They have different information. So is that generally true for these results? That only is when you see that it's not matching?
Yeah, mostly.
Okay.
So so in addition to the absolute, I really want to show that this RPI property can be true in practice as well in this like heuristic sort of implementation, but follow the design principle design. So here we compare how the algorithm performs on the different beta values. Right, and then I'm going to compare how it works with the absolute version and the relative version. So here the orange one, or the kind of red-orange one, denotes the performance of the absolute version, and the blue one denotes the relative version, and the green one is the performance of the behavior policy. So in all these experiments on the data set that I show you here, like we found that the relative version outperforms the behavior policy for all the beta value except for very large ones, and that is exactly what our theory predicts. Right. Remember that we need the beta to be sublinear in number of n's. It cannot be super large, otherwise the noise will blow up. Right. So with this, we see this is true. And roughly the reason why it's true again is due to imitation learning. If I tune this algorithm that I implement with like very small beta value, it's kind of doing this imitation learning with GAN. Yeah.
Figure K doesn't seem to be true.
Yeah. So there is like an error bar in there. Yeah. And then also that's one, that kind of the most difficult data set in all this. And we kind of just like empirical approximation, but it's like roughly true almost. Yeah, this is something that's super surprising to us because yeah, we don't really have a theory already. It's kind of very like hesitant to us to really to see whether that's true empirically or not. And it's surprising that yeah, it actually turned out to be true. So which is really nice. And also we see that this is not true for the absolute version. So like if you set the beta to be round to be very small, it can degrade very badly. Okay, so yeah, let me summarize the talk. So basically today I talk about a game-theoretic approach to offline RL, and it's based on the idea of having a learner to compete with an adversary in a two-player game or Stackelberg game. And we show that this approach can be used to systematically design a algorithm for offline RL with provable guarantees, and they also have very like really usable practical approximations. So I talked about two versions and mostly focus on the model 3 version, and they kind of just differ in terms of their objective file. And I show both cases have like learning optimality guarantees. If you choose a right beta value with this magical number, then you can basically compare with the best cover policy as any other offline RL policy algorithm can do. But they are kind of being less pessimistic than their pointwise version. For the relative one, we have this extra nice property called RPI, and then which allows it to kind of be robust to hyperparameter selection, right? And these properties are kind of useful to applications where the decisions can be super critical. You don't want to, let's say, make a mistake, like let's say in the healthcare applications. And it can also sometimes be used to do online hyperparameter tuning. If your application, you allow, let's say, running a policy that is better than the behavior policy in online, then what I can do is that I can start from beta equal to 0 and gradually increase the beta to kind of like fine tune the performance of the algorithm. And I'm guaranteed that while doing so, I'm not going to have any policy performance degradation. If that's allowed, then you can use this property to do extra fine tuning if you want. Okay, so this is the last slide. So I want to just briefly mention that all the things I talked about have a very natural extension to the model-based case. And the thing you'll need to do is just to change what a hypothesis is. So in the model 3, a hypothesis is a function of state and action. In the model-based one, a hypothesis will naturally be a model, right? And then the regularization to enforce data consistency will be kind of like model fitting error, like these are reward difference and log likelihood. So for the absolute pessimism again, the natural definition of this objective will be just the absolute performance of a policy under this model, right? And this is actually a known algorithm, which is a follow-up work of our original paper, and this algorithm is called CPPO. We can do the same for the relative version. And in that case, the objective will be just like the performance difference under the model. And as I mentioned, that in this version, it's even nicer that you can even change this mu to a different policy that you have as a baseline rather than sticking with the mu. And you also have like a smaller, like you remove from the statistical error that we have seen in RPI. So this is ongoing work that we are about to kind of put online very soon. Yeah, but finally, I want to mention that I feel like there are still like many choices that we can explore in this space. In let's say choosing phi, choosing this regularization, choosing what a hypothesis class is, and also like choosing how we actually optimize for this two-player game. Right? What I present is very preliminary and kind of like natural choices that you probably will try in the first step. But I think like there are still like many possibilities that we can explore in this space, and I think there are like very interesting research directions. Yeah, so finally, if you are interested, I will invite you to read the papers, and then you can, if you really want to run the experiments, I'm not sure you will, but you can find the code online, open source as well. Yeah, thank you.
How do you deal with that in the model 3 case, the Bellman operator is inside the square?
Oh yeah. So the real we need to kind of approximate it by the regret in the regression in the theory. So you kind of like compare. So
min-max formulation.
Yeah, you can do min-max, or you can do, let's say I have a target and then I kind of like minimize basically the excessive error. So basically I have the square error and minimize, let's say that versus the yeah, it's a
non-auxiliary variable.
Yeah. So these FF tend to kind of have basically like the kind of the right vertical space for the in the theory. Empirically, we just use the tucking net. Yeah. So that part can there's a square tensor you can directly do it, but I'm showing this for simplicity.
Do you have like some overall intuition that you can give about how this pessimism along, like just in the, that's why I know the robust part, that's the first set of results. What is it giving you compared to the existing one?
You mean,
Yeah.
This part?
Yeah.
Yeah, so the main difference is basically it's in a very high level is how you measure the support. So most existing algorithms measure the support based on the kind of the data density. So for example, I can only, let's say, compute with policy whose data density ratio compared with the behavior policy is bounded. Right? You define a support based on the density. Whereas here we kind of define a support based on, let's say, how much basically the region where your error will generate. Right. So let's say if in this is not a very good example in here. Suppose in this color example, all your functions agrees on the right hand side. This is a whole like collapse, right? So that would be essentially like places where your function agrees based on your as a hypothesis class, but you have zero data density. And so this version can basically allows you to generalize to those regions as well, and basically you don't really measure the error in there. On the other hand, if I do something that's more close to, let's say, trying to make my policies stay close to the data distribution or some truncation based on the kind of measure, then I can't have a tighter, a smaller region that I can actually generalize. So that's kind of the main difference in a bigger picture. There's for both relative and absolute version, the guarantees are almost similar for the performance in the regard.
Thank you, speaker.